Hello, welcome back to my channel. Today we will discuss on experiment 6, standing wave. So the objective of this experiment is to investigate the standing wave formed in a straight string. Okay, so based on this diagram, there is a string and this string is tied on the metal rod. This is connected with alternating supply, is alternating current. So what happens is when we on this straight string, it will vibrate. So when one end of the straight string is vibrate, a traveling wave moves along the string and it will reflect back from the other end. Okay, so what happens is it will travel to the right and then it will reflect back to the left. Therefore, it will form a stationary wave. Okay, so sometimes we will call standing wave and sometimes we will call stationary wave. Okay, so standing wave and stationary wave are referring to the same things. So this is one of the application of the standing wave where we have not where the amplitude equals to 0. Okay, when the amplitude is maximum, here this is the maximum point. This is we call NT0. Okay, so NT0 is when the amplitude, the displacement is maximum. The frequency of this standing wave is F equals to 1 over 2L square root tension over mu. Okay, if we square both sides, we will get tension equals to 4 mu F square L square. Okay, so for this experiment, we are going to plot T versus L square. Okay, so meaning that later, if you compare with y equals to mx plus c, y-axis is tension, x-axis is the L square, meaning that the gradient is equal to 4 mu times the frequency square. Okay, since we want to plot T versus L square, so we need to find tension and also L square. Okay, from this diagram, okay, here is the slotted mass. So when we insert the slotted mass, what happens is this straight string will vibrate. Okay, so we want to measure what is the length. Okay, length here we are referring from knot to knot. So this is the length. Okay, so we will take length here is from knot to knot. Okay, so the data is given here, the mass and also the length. Okay, so we notice that when the mass is increasing, the length also will increase. Next, we are going to find L square. Okay, where we already obtained L in cm. Okay, so we want to find L square, so we directly convert it into meter. Okay, it's easier for us to plot graph later. Okay, so 19.2 in cm, we use 19.2 times 10 to the power of negative 2, and then you square it up, you will get 0.037. So this is your L square. And tension, how can we find tensions? We know that from this slotted mass here, okay, the string here, the tension is acting upward and mg is acting downward. Okay, so for this slotted mass, we know that T is equal to mg. Okay, so the tension here along the string are the same because they are referring to the same string. Okay, so therefore tension we use T equals to mg to find, and the unit is in Newton. Okay, so remember m here we must convert it into kg, and g is actually the gravitational acceleration 9.81. Okay, so 10 gram here we need to convert it into 0.01, and then we times 9.81, so you will get 0.098. Okay, so L square and T is a secondary data, meaning that these two data you must either 2 or 3 decimal places only. Okay, here from the data given, delta M is given here and also the frequency F is given 50 Hz. So later we will substitute it into the equations. Okay, so we look at the observation here. So the first step, what should we do is we need to find the centroid. Okay, so remember you need to find the centroid X and also Y. X-axis is actually our L square and Y-axis is actually tension. Okay, so you need to find the mean for L square and also tension. And remember, okay, L square, because just now L square is in 3 decimal places and tension also 3 decimal places. So therefore, the answer is 3 decimal places. And remember to write meter square. And tension also 3 decimal places. And remember, you need to write Newton. Okay, so after we obtain the centroid, you plot into our graph. So this is the centroid. Okay, remember to circle it up. Okay, so this is the centroid. Okay, next we go to the graph. Okay, so for graph part, the first one you must write the title. Next you must label y-axis tension in Newton, x-axis L square in meter square. Okay, the third part is you must plot the centroid. Okay, so you must circle it up. Okay, next one is you must have the 6 points. So 1, 2, 3, 4, 5, 6. Okay, all the 6 points, if you plot correctly, you will get another 2 points. Okay, and then the best fit line. Okay, so if you draw the best fit line, usually best fit line you must passing through the centroid and as many points as possible. Okay, and balance on both sides. Okay, next one is the gradient, the triangle of the gradient. So the triangle of the gradient here, okay, remember to draw 8 cm on y-axis, similar for x-axis also 8 cm. Okay, next one is the scales that we use. Okay, so here if let's say I'm using for x-axis is 0.05, here will be 0.10, 0.15, 0.20 and so on. Okay, so the uncertainty is half of the smallest division, so it's 0.05 over 20. So therefore, we will get 0.05 over 20. So we will get 0.0025. 4 decimal places. Okay, for y-axis, 0.1 over half of the smallest scale, so we straight away divide 20. So 0.1 over 20, you will get 0.005, 3 decimal places. For example, let's say my value here, okay, this is example only. Okay, so let's say my value here for x-axis, for example, is 0.17. So I must write 0.1700. For my y-axis, for example, 0.55, and then I must write 0.550. Okay, so similar, x-axis, for example, 0.03, so I must write 0.0300, and for y-axis is equal to 0.090. Okay, so I will substitute inside here y2 minus y1 over x2 minus x1, where y2 is 0.550 and y1 is 0.090. x2 is 0.1700 minus 0.0300. Okay, so therefore the answer for the gradient is equals to 3.2857. Okay, so how many decimal places? Okay, we might refer here. Okay, 0.550 is 3 significant figure. 0.090 is 2 significant figure. 0.1700 is 4 significant figure, and 0.0300 is 3 significant figure. So therefore, we must write at least 2 significant figure or 2 plus 1. Okay, so we can write 1, 2, 3. Okay, so if I round off, I will get 3.29. Okay, 1, 2, 3, 3 significant figure. Okay, because we can allow 2 plus 1. Okay, so 3.29, what is the unit? Since y is in Newton, okay, Newton we can write it as kg meter per second square, and then L square is in meter square. So therefore, the unit for the gradient is equals to kg per meter per second square. Okay, so this is the unit for the gradient. Okay, after that, we already obtained from the data give the uncertainty of the gradient. So this is the delta m equals to 0.3418911. Okay, but we will not write too many decimal places. So usually we will follow back from the gradient. We obtain 2 decimal places. So therefore our delta m, we just follow back 0.34. Okay, we follow back the decimal places. Okay, so we can write m plus minus delta m is equal to 3.29 plus minus 0.34. Okay, so meaning that the gradient that we get is equal to 2 decimal places. So our uncertainty also will follow 2 decimal places. Okay, and you must write the unit kg per meter per second square. Okay, so remember to write the unit as well correctly. For compare equations with the gradient, so from the equations we know that tension is equal to 4 mu f square L square, and we plot T against L square. So therefore we know that gradient is actually equal to 4 mu f square. Okay, so for this experiment we want to find mu. So mu will equal to the gradient over 4 times the frequency square. Okay, so you substitute the gradient here is 3.29 over 4, and the frequency just now already give you 50 Hertz, so we just substitute into the equation. 50 Hertz is given. Okay, so therefore mu we will get 3.29 times 10 to the power of negative 4, and the unit is in kg per meter. Okay, next one, find the uncertainty of the mass per unit length. Okay, meaning that we want to find delta mu. Okay, so from the equation, mu is equal to m over 4 f square. So therefore, delta mu over mu is equal to delta m over m. The uncertainty of the mass per unit length, delta mu is equal to delta m over m times mu. Okay, so delta m is equal to 0.34, gradient is equal to 3.29, and mu we get 3.29 times 10 to the power of negative 4. Therefore, delta mu is equal to 0.34 times 10 to the power of negative 4 kg per meter. Okay, so our result is equal to 3.29 plus minus 0.34 times 10 to the power of negative 4 kg per meter. Okay, so remember, the uncertainty here must only allow one significant figure. Okay, so therefore our uncertainty we should write as 0.3. Okay, so since the uncertainty is one decimal place, so therefore our result we must also follow back one decimal place. So we must write our result equals to 3.3. So the result is 3.3 plus minus 0.3 times 10 to the power of negative 4 kg per meter. Okay, last step is to find the percentage of uncertainty, where we use delta mu over mu times 100%, where delta mu is equal to 0.3 times 10 to the power of negative 4, and mu is 3.3 times 10 to the power of negative 4, then we times 100%. Okay, so negative 4 we can cancel off. Percentage of uncertainty is equal to 9.09%. Okay, next we will go to discussion part, where discussion part usually we will have 3 parts: report the finding, errors and mistakes, and then step 3 is the precaution or ways to overcome. So experimental value, remember you must report mu plus minus delta mu. Okay, so just now our value is 3.3 plus minus 0.3 times 10 to the power of negative 4, and then the unit is kg per meter, and then percentage of difference is equal to 9.09%. Okay, so you must report out what is your finding, and then you must have at least write 2 errors or mistake, and then 2 precaution step or ways to overcome. Okay, after that, for conclusion part, you must make conclusion for your finding based on the learning outcome. Okay, so you must report what is your finding based on the discussion part. That's all for this video. Thank you for watching. Bye.